All right, getting into our next lesson here about graphing inequalities in two variables. So starting off, a little warm-up, determine if each point is a solution to y is greater than x, y is less than x, or y is equal to x. Well, looking at number 1, we got an x of 8 and a y of negative 2, so this would be a case of y being less than x. For number 2, x of 0, y of 7, this would be a case of y being greater than x. For 3, negative 1 and negative 1, those are obviously equal, so y equal to x. And for number 4, negative 4 for x, negative 3 for y. Negative 3 is greater than negative 4, so this would be y greater than x. And 9, back to being equal. And then for our last one, negative 3 for x, and then we got negative 10 for y, so negative 3 is greater, so this would be y is less than x. All right, so we're going to be looking at today, like I mentioned, graphing inequalities in two variables. Key terms we'll be seeing half plane and boundary line. All right, on the getting started activity, consider each solution statement, compare the solution statements. What does each one mean? So we're just going to go through each inequality symbols and talk about each one and what they mean. So obviously equals means just like it sounds like, that the two values are equal to each other. We have greater than, we read it from left to right, so that open side faces the left, so this is a greater than sign. And then before we get to the less than, I like to include with that the greater than or equal to sign. And then it'll turn the other way and we got a less than sign and a less than or equal to sign. All right, for number 2, you can take a moment, give that a shot. Just choose one of those solution statements, then modify scenario so the resulting interpretation is one of the 4 solution statements. So come up with a scenario that would fit one of those statements and write the statement that it would apply to and write out your scenario, just for a little extra practice on coming up with application for inequalities. All right, moving on to our next page, activity 4.1. It says Coach Burvis is analyzing the scoring pattern of players on his basketball team. Benna is averaging 20 points per game from scoring on 2-point and 3-point shots. Obviously, the two types of shots we can make, 2-pointers and 3-pointers. If she scores six 2-point shots and 2 3-point shots, will Benna made her point average per game. So in other words, we got 2 times 6 2-point shots plus 3-point shots she has 2 of. We need to know what that will equal to. Well, if we simplify that, we get 12 plus 6 and we get 18. So that is not meeting her 20-point average. So this would be a no. If we want to write that as an inequality, 18 would be less than 20. For B, if she scores 7 2-point shots, so 2 times 7, and 2 3-point shots, so 3 times 2, we want to know what that would equal to. So if we simplify that, we are going to get 20. So yes, now she does equal her, Benna doesn't equal their average. 20 equals 20, so we'll write it the number. You can either write it as an equal, if you wanted to do it as an inequality sign, as long as we had that or equal to, it would be a true statement. Okay, C, 7 2-point shots and 4 3-point shots. Well, if we simplify that one, we're going to get 26. So that was a yes also. I forgot to write yes with this one up here. So yes did meet the scoring average of 20 because 26 is greater than 20. So if we wanted to write an equation to represent the number of 2-point shots and the number of 3-point shots that total 20, we could call x 2 pointers. So we could say 2 times x plus 3 times y, y would be number of 3 pointers, equals 20 points. So if we wanted to graph that now, 2 ways we could graph it. We could graph the intercepts, or we could solve for y and graph it. Either way would work. I'm going to graph it using the intercepts method. So if we have 2x plus 3y equals 20, if I want the x-intercept, the y becomes 0, and I'm left with 2x equals 20. Divide by 2, and I get x equals 10 for an x-intercept. So I'm going to count by, skip a line, count by 2s, 4, 6, 8, 10. So I'm going to say my y-intercept's right there. Or sorry, my x-intercept. And then for my y-intercept, when we plug in 0 for x, we're left with 3y equals 20. So if we're going to divide 20 by 3, I should say, and we're going to get 6.67. So there's our y-intercept. So we're going to have to estimate it just a little bit. So I'll say 2, 4, 6, 8, 6.67 be about right there. Oh. Let me fix that. There we go. About right there. So we can see our line would look about like that. Yeah, on to the next page. Coach Purvis believes that Danvers High School can win the district playoffs if Benna scores at least 20 points per game. So how can we write an equation? How can we rewrite the equation we wrote on question 2 to represent that Benna must score at least 20 points? Well, the key with at least is we were talking about using a greater than or equal to sign. So if we use a greater than equal to sign and make that value, so Benna's points needs to be greater than or equal to 20. So if we wrote that as an inequality now from our equation, 2x plus 3y would be greater than or equal to 20. Okay, so using that, on to number 5, complete the table of values. Then add the order pairs and the pairs to the table and from the table to the graph back on question 3. If the number of total points does not meet or exceed Benna's point per game average, use an X to plot the point. If the number of total points scored meets or exceeds the point average per game, use a dot to plot the point. So if we plug in our values here, again, 2 pointers times 2, 3 pointers times 3. So for each one of those, you could think of this times 2 times 3, we are going to get a number of points scored would be 11, then 15, 17, 22, 24, and 33. So there would be all our point totals based off each one of those. And again, each one of those you just multiply 2 pointers by 2, 3 pointers by 3 to get those points. Now, if we were going to go mark those points, obviously these 3 do not meet the point average. So we got a point of 4-1, mark with an X, 6-1, again marked with an X, and then 7-1, also marked with an X. Now the points that do meet the point average are going to mark with a dot back on that graph, 8-2. Oh, let me try that again. 8-2 would be here. There we go. All right, 8-2, 6-4. And then 9-5. So 9-5 would be about right here. Okay, so we can see all those points are above the line, which makes sense with our inequality being a greater than or equal to. All those points fall above the line. So what do we notice about the graph? It'd say all the points that exceed the 20. Well, if you did not get that, just rewind the video. I hit the delete button on accident again. I'm going to rewrite for number 6. So it was all the points that exceed the 20 point per game average are above the line. And again, I'll go back in quickly and just fill these numbers in. If you did not get those and did not want to rewind, we'll just take a second. So 24 and then 33. And then going back up, our inequality was 2x plus 3y is greater than or equal to 20. And that's because Benna's points were greater than or equal to the average, is what we use to write that inequality. Okay, for 7, what can we interpret about the solutions of the inequality from the graph? Well, that line is the boundary, and the points that don't satisfy it, the inequality, are below the line. So we could say the line is the boundary, points that don't satisfy the inequality fall below the line. Okay, 8 says choose a different order pair located above the line and a different order pair that is located below the graph. And how do these points confirm your interpretation? Well, if we find one above the line, it's going to be one that does fit the inequality. So for example, let's say 9, 6. So 9 2-pointers and 6 3-pointers. We need that to be greater than or equal to 20. And that's going to give you 18 plus 18, which is 36. So Benna definitely exceeded that average point total with 36 is greater than or equal to 20. Then, of course, you could find one that does not meet it. Let's say something simple like 1, 1. So 2 times 1 plus 3 times 1 would give us 5 is greater than or equal to 20, which is not true. So that point does not satisfy the solution set to that inequality. So 9 says shade the side of the graph that contains the combination of shots that are greater than or equal to Benna's point per game average. So this is how we showed the solution set for an inequality. Essentially, if we go back to our graph, we would shade above that line since it's a greater than inequality. And 10, how do the solutions of the linear equation 2x plus 3y equal 20 differ from the solutions of the linear inequality 2x plus 3y is greater than or equal to 20? Well, equal is only the points on the line. Greater than or equal to is points on or above the line. Okay, 11. Does the ordered pair 6.5 pot 5.5 make sense as a solution in the context of the problem situation? So, two situations here. The point itself does satisfy the inequality, but in context, when we're applying it to this situation, where X and Y are related to shots, basketball shots made, you obviously can't make 6.5 2-pointers, or you can't make 5.5 3-pointers. So no, it doesn't make sense, and it's simply because you cannot make half a shot. I'll put make part of a shot. So linear inequalities can take different forms. Each of the linear inequalities in two variables shown represents a different relationship between the variables. So this is showing the 4 different inequality signs we could have. We could have a less than sign, less than or equal to, a greater than sign, or a greater than or equal to sign. Okay, so on to activity 4.2, determining the graphs of linear inequalities. The graph of a linear inequality in 2 variables is a half plane or half of a coordinate plane. A boundary line determined by the inequality divides the plane into 2 half planes. The inequality symbol indicates which half plane contains the solution. So which side of the line contains the solution. These solutions are represented by shading the appropriate half plane. So greater than, we're going to shade above the line, less than, we're going to shade below the line. So it says, consider the linear equality y is greater than or equal to, or greater than, sorry, not equal to, y is greater than 4x minus 6. The boundary line that divides the plane is determined as if it was an equation, y equals 4x minus 6. But, as one says, should the boundary line in this graph be a solid or dashed line? Okay, so we talked about we shade above the line if it's greater than, below the line if it's less than. Now with the line itself, if it doesn't, your inequality sign does not have an or equal to, it's going to be a dotted line. So in other words, these 2 symbols here, less than or greater than sign, are going to be dotted lines, and a greater than or equal to or less than or equal to are going to be solid lines. Another way to think of it is if the word or equal is involved, you write an equation, has an equal, greater than or equal to, less than or equal to, you're going to make a solid line. If the word equal is not involved, we're dealing with a dotted line. So if we want to graph this equation, or this inequality, y equals 4x minus 6, we have a y-intercept of negative 6, slope of 4, so up 1, 2, 3, 4, right 1. And as we mentioned, this does not have an or equal to, so this is going to be a dotted line. So just basically showing that it's not a solid line. And our sign is a greater than sign. It's y is greater than or equal to, well, greater than, not or equal to, sorry, I keep saying that, greater than 4x minus 6, so we're going to be above that line. So above that line, I'm going to switch colors here, is going to be on this side. If you get stuck on which side is above or below as the line gets more vertical, it can get a little tricky. You look at your y-axis. For instance, when I'm looking at this y-axis, number above it is 2, number below it might be negative 8. Which one's greater than? It'd be the side with the 2, so that's the side we are shading on, the greater than side. Okay, so we already decided which half plane to shade. I already showed you we're going to shade on the greater than side, which is the side above it. So it wants to know is 0, 0 solution. So if we go look at 0, 0, yes, it's on the side of the line that it is shaded. So yes, on the shaded side. Okay, and we already shaded the correct half plane. So now down to 4, it wants us to match each graph to one of the inequalities given. In part D, graph the inequality that was not graphed in parts A through C. Okay, well, when we're looking at, let's say, the first inequality there, y is greater than or equal to 1/2 x minus 3. So the first thing I look at to narrow it down is it has an or equal to, so it's got to be a solid line. That rules out A and C. So if I go look at B, that has a y-intercept of negative 3. That's correct. A slope of 1/2, up 1, right 2. So that matches. But that inequality sign, if we look here, is a greater than sign. That graph is shaded below the line, not above the line on letter B. So that can't match up with it. So it looks like that first graph, or that first equation, is going to be the one we're going to graph ourselves. So we'll skip past that one for now. We'll come back to it. If we look at this second one here to the right, this also has an or equal to, so it better be B. It's the only other one with a solid line. Y-intercept of negative 3, slope of 1/2, so it's just like the last one, but this one has a less than sign. So it's shaded below it, it is correct. So I'm going to draw a little line here, just match them that way. Okay, if we go down to the bottom left one, So now it's one of the two. It's got to be A or C. It's got a dotted line because neither one of those signs has an or equal to. So both of them have a y-intercept of -3. Both of them have a slope of 1/2 still. So it just comes down to above or below the line. So this bottom left one has a greater than sign. So it'd be shaded above the line, which is what A is showing us. And that leaves our last one. This one better be C. And it is shaded below the line with a less than sign. So that does match up. So if we wanted to graph the missing one, D down here, y-intercept of -3 again. Now you notice all of these graphs looks like they counted by maybe 2s, it looks like. So yeah, because they skipped a line. So we're going to put it to match those. We're going to put it right here. And then up 1, right 2. So it's going to look just like the same slope as the other one because they all have a slope of 1/2. This one does have the or equal to, so it's a solid line. And this one is a greater than symbol, so our shading is above the line. So there would be our graph that matches that first equation to graph D, the only one that was not listed. All right, so moving on to the next page, we're going to graph some of these inequalities. So for 5A here, we have a y-intercept of 3 and a slope of 1. So we're going up 1, right 1. This one does not have the or equal to, so it is a dotted line. Now, if I can put points just moving up 1, right 1, I just like to put all the points on the line and go ahead and put my arrows on the end of it. Call that my dotted line. There's enough points there. It works as a dotted or dashed, you might say, line. Now, this is a greater than sign we're looking at. So we're going to shade above the line. So there would be our shaded side above it. If we go down to B, B has a y-intercept of 4. And a slope of -1/3, so down 1, right 3. Now this one does have the or equal to, so we need to draw our solid line. And it's a less than symbol, so it's going to be all the shaded area below the line. So there would be our graph on B. And C is going to take a little bit of work. It's not solved for Y yet, so we got to solve it for Y ourselves. So first we're going to subtract that 2x over. So we get -y is less than -2x plus 4. And then we need positive y. So what we're doing is dividing by -1, which we talked about before, flips your inequality sign around. So it becomes positive 2x minus 4. So a y-intercept of -4, slope of 2. And this one is a dotted or dashed line because we do not have the or equal to. And it is a greater than sign after we flipped it over because of the dividing by -1. So our shaded area is above that line. Okay, the next page, just recapping everything we just used to graph those on the previous page. It says previously you've written a linear equation given various representations, including 2 points, 1 point, and a slope, a table of values, or a graph. We can use that same approach when we're writing a linear inequality. So if we want to write a linear inequality from a graph, think of it as reverse of what we were just doing. We can look at the line, determine if it's solid or dotted, or is it shaded above or below it to see if it's a greater than or less than sign, and then pick out my y-intercept and my slope. So for instance, looking at this graph, we can pick out the inequality sign simply by knowing where's the shading, so it's above it, so I know it's a greater than sign, and it's a solid line, so I know it's going to be greater than or equal to. And then it looks like your y-intercept is at -5, so we know we're going to have a -5 on the end. So all we need left is our slope, and this is going down from left to right, so it's a negative slope, and we're going down 3, right 2. So -3 over 2 would be our slope. So there's our full inequality, just like they're showing here. All right, so on the next page, we're going to do just that. We are going to write the inequalities given the graphs of these various linear inequalities with the shading done. So for A, Picking out my sign, it's shaded below the line, so I know it's a less than, and it doesn't have a solid line, so it's going to be dotted. My y-intercept looks like it's at 2, so I know I'm going to end with a plus 2, and then I just need my slope. So it's a positive slope going up from left to right. 1, 2, 3, right 1. So y equals 3x. Or did I count wrong? I think I counted wrong. 1 second. I think I skipped the line counting. So up 1, 2, 3, 4, right 1. There we go. So 4x plus 2. Should have zoomed in a little bit more. Okay, if we go over to b, b is now shaded above the line. So we know it's a greater than sign. It is a solid line, so we got the or equal to. This one looks like it has a y-intercept at -3. And our slope is going up 1, right 2. So we get 1/2 x minus 3. So there's our inequality for that one. And then C, this one is shaded below, so it's a less than sign. It does not have the or equal to, so it's a dotted line, so it doesn't have the or equal to. We got a y-intercept at -2 and a slope that's positive again. Here's a point. We're going up 1, 2, 3, right 1, 2, 3, 4. So we get y is greater than or equal to, or sorry, why do I keep saying that? Y is less than 3/4 x minus 2. I'm looking at a sign on another page coming up here. All right, so skipping all the way to past 4.3, we're going to go wrap it up here on the talk here at the end to summarize everything together. They gave us a graph with just an equal sign, x plus y equals 20, and wants us to use that graph to describe how we could graph if we were changed to these various inequalities. So first of all, with number 1, if we were to solve that for y and subtract x, we're going to get y is less than -x plus 12. So that would be a dotted line shaded below that line. So shaded below. Now, if we want to pick a point to test, I think the easiest point to always pick is 0, 0. If I plug in 0, 0 there, I'm going to get 0 is less than 12, which is true. And 0, 0 would then fall below that line in the shaded area. So that makes sense. Okay, for number 2, same thing. If we solve for y and subtract x over, we're going to get y is less than or equal to -x plus 12. So again, if we wanted to plug it or right where we're shading, first of all, that's going to be a solid line because it's got the or equal to, and this one is also still shaded below because it's a less than sign. And again, I'm going to test 0, 0. So this point right here on the graph, we're shaded below that line, so it should still work. We plug that in, you're going to get 0 is less than or equal to 12 again. So that still works. And for the last one, if we solve for y, we're going to subtract x, and we're going to get y is greater than -x plus 12. So that would be a dotted line again, just like the first one, and it's greater than, so our shading is going to be above this line. So again, if I'm going to test 0, 0, 0, 0 shouldn't work because we're going to shade above that line now up here. So I plug those in, I get 0 is greater than 12, which is not true. So that's why 0, 0 below that line does not fall into the solution set.